Every deep-sea documentary paints this creature as a blood-red nightmare of the abyss, a terrifying predator named the vampire squid from hell. We highlight its glowing blue eyes, its webbed, cloak-like arms, and its ominous shadow, suggesting it stalks the dark zone like a silent, bloodthirsty hunter. If you watch the cuttlefish episode, you remember how they debate about matching the color of their reef. Today, we look at a deep-sea relative that doesn't match background patterns, because in the pitch black, it must erase its own shadow. They discovered that instead of hunting in the dark, the vampire squid uses a grid of bioluminescent light organs on its underside to erase its own silhouette, matching the downwelling light from above. Stay for the oxygen minimum survival reveal. This animal survives in near-zero oxygen zones without a high-capacity cardiovascular system. To understand the reality of the deep ocean, we must dismantle the myths we have brought down from the surface. In 1903, German marine biologist Carl Chun dredged up a strange creature from the deep mesopelagic zone. It was a dark, webbed organism with glowing blue eyes, which Chun named Vampiroteuthis infernaalis, the vampire squid from hell. For over a century, popular nature documentaries painted this creature as a ferocious, blood-sucking monster of the abyss. Its menacing appearance and dark red coloration suggested a silent hunter stalking prey in the pitch black. But this terrifying reputation was based entirely on its appearance, not on its actual ecology or behavior. When researchers finally developed the technology to observe the animal in its natural habitat, they found something very different. They realized they were looking at a gentle, passive survivor that operates on a completely different logic. To survive in the deep ocean, an animal must adapt to extreme physics and limited resources. It cannot afford the high-energy hunting strategies of shallow-water species. Every move must be calculated, every calorie conserved, and every survival strategy optimized for efficiency. And the first clue to this efficiency lies in its taxonomic classification, which baffled biologists for decades. At first glance, the animal resembles a typical squid, with its 10 arms and jet propulsion system. But a closer look at its anatomy and genetics revealed a major discrepancy in its lineage. Insight 1. Genetic analysis by Sanchez et al. In PeerJ proved that the vampire squid is not a true squid, but a unique lineage closer to octopuses. It is the sole survivor of an ancient order of cephalopods known as the Vampiromorpha. Its lineage diverged from true squids and octopuses over 300 million years ago, in the late Paleozoic era. This means the vampire squid was already drifting in the deep oceans before the first dinosaurs walked the earth. While true squids evolved into active, fast-swimming predators, the vampiromorphs took a completely different path. They retreated to the deep mesopelagic zone, escaping the intense competition of the sunlit waters. In these deep waters, they preserved ancient features that true squids lost long ago. These features include a pair of retractile sensory filaments that are unique to this species. To understand why they retreated here, we must understand the severe physical reality of this deep biome. It is a region where the sun is reduced to a faint, directional glow, and shadows are the ultimate threat. In the mesopelagic zone, there are no rocks or plants to hide behind. The water column is completely empty. Predators swimming in the deeper layers look upward, searching for silhouettes cast by animals swimming above them. Any animal that blocks the downwelling light casts a sharp shadow, revealing its location to hungry hunters. To survive, deep-sea organisms must find a way to become completely transparent or light-emitting. The vampire squid solved this problem not by becoming clear, but by active counter-illumination. Wait, how can an animal produce light that perfectly cancels its own shadow? It requires a sophisticated array of light-emitting organs distributed across the underside of the mantle. If you want to keep exploring the hidden intelligence and bizarre biology of the oceans, subscribe to PHANERON today. These organs, called photophores, produce a cold, bioluminescent light through a chemical reaction. Unlike simple light-emitting spots, these photophores are equipped with lenses and color filters. The vampire squid can neurologically control the intensity and angle of the light they produce. This allows them to adjust their light output to match the changing light filtering down from the surface. If a cloud passes over the distant sun, the light in the twilight zone dims slightly. The vampire squid instantly detects this change and dims its photophores to match the new background. This real-time adjustment requires constant visual monitoring and precise neural coordination. If the light emitted is too bright, the squid becomes a beacon. If it is too dim, the shadow remains. This balance is achieved through a network of photoreceptors that measure both downwelling and emitted light. The result is a perfect shadowless camouflage that hides the squid from predators looking up from below. To a predator looking up, the squid is indistinguishable from the ambient blue light of the sea. It is a dynamic, active performance that turns the skin into a cloaking device. Insight 2. Richard Young and C. Roper showed in Science that vampire squids use bioluminescent counter-illumination, erasing their silhouette to match downwelling light. This discovery proved that deep-sea camouflage is just as active and complex as shallow water camouflage. But while shallow water species hide from eyes that see color, the vampire squid hides from eyes that detect contrast. To achieve this, they must use an analogy that we have only recently invented in our own technology. We often think of camouflage as a passive matching of background textures, like a chameleon on a branch. It is like a pair of Bose Quiet Comfort headphones generating anti-noise waves to cancel out external sounds, except the vampire squid is generating anti-shadow light to cancel out its own silhouette. The headphones measure incoming sound waves and create an inverted wave to neutralize them. In the exact same way, the vampire squid measures incoming downwelling light waves and generates matching light to neutralize its shadow. This active cancellation is what allows them to remain completely invisible in an empty water column. But this light-producing camouflage is only half of their survival story. To live in this zone permanently, they had to solve a second, even more suffocating problem. They had to adapt to a region of the ocean where oxygen is almost entirely absent. This region is known as the oxygen minimum zone, a suffocating barrier for most marine life. Here, oxygen levels drop to less than 10% of what is found at the surface. Active predators like true squids cannot survive here. Their high-energy metabolism would suffocate them in minutes. Suffocate. How can an active cephalopod thrive in a zone with near-zero oxygen? The answer lies in a complete redesign of their respiratory physiology and metabolic rate. First, their blood is uniquely adapted to bind oxygen with extraordinary efficiency. They use a copper-based protein called hemocyanin, which gives their blood a distinct blue color. Their hemocyanin has the highest oxygen affinity of any cephalopod ever measured. Insight 3, Brad Seibel proved in the Journal of Experimental Biology that vampire squids survive in low oxygen due to high-affinity hemocyanin blue blood and massive gills. This high-affinity blood allows them to extract oxygen from waters that would be lethal to other species. To support this extraction, they have evolved gills with an exceptionally large surface area. These massive gills capture every stray molecule of oxygen dissolved in the surrounding water. But high-efficiency breathing is only useful if you also minimize your oxygen consumption. The vampire squid possesses the lowest metabolic rate of any cephalopod known to science. Their muscles are composed of slow-twitch fibers that consume minimal energy. They do not run or chase. They spend most of their lives gently drifting in the current. This low-energy lifestyle is supported by a third, highly counterintuitive adaptation. A low-energy metabolism is useless if you must spend calories chasing fast-swimming prey. So the vampire squid abandoned predatory hunting entirely. It is the only cephalopod known to science that is not an active carnivore. Instead, it has adapted to feed on the waste of the upper ocean layers. It feeds on marine snow, a constant drizzle of dead plankton, fecal pellets, and organic debris. This debris falls from the rich, sunlit surface waters down into the dark abyss. To collect this falling food, they use their unique retractile filaments. These filaments are covered in microscopic sensory hairs and sticky mucus cells. The squid extends these filaments out into the water column, acting like a passive drift net. As marine snow falls, the organic particles stick to the mucus-covered filaments. Insight 4. Henk Jan Hoving and Bruce Robison documented in the Proceedings of the Royal Society B that vampire squids feed on marine snow using two retractile sensory filaments. Once the filament is coated in debris, the squid draws it back through its webbed arms. It cleans the filament using its arms, scraping the collected organic matter into its mouth. They use their own mucus to bind the loose organic particles into a tight, swallowable bolus. This passive feeding strategy requires almost zero muscular effort. They do not need to swim fast, chase prey, or fight competitors. Glowing shield. What happens when a predator does manage to locate this passive creature in the dark? If a predator approaches, the vampire squid cannot escape using fast jet propulsion. And it cannot use traditional ink, which is completely invisible in the pitch blackness of the abyss. So they have evolved a spectacular, light-based defense mechanism. They turn their entire body inside out, wrapping their webbed arms over their mantle. This is known as the pineapple posture, which hides their vital organs and exposes soft spikes. These spikes, or cirri, look menacing, but are actually soft and harmless sensory structures. If the predator persists, the squid deploys its ultimate defensive weapon. It discharges a sticky cloud of mucus from the tips of its arms. This mucus is not dark like ink. It is filled with thousands of glowing bioluminescent orbs. Insight 5. Bruce Robison's team showed in the Biological Bulletin that vampire squids expel a glowing cloud of bioluminescent mucus containing luminous orbs to dazzle predators. The glowing cloud hangs in the water, distracting and dazzling the predator's eyes. While the predator is focused on the glowing decoy, the squid turns off its lights. It drifts away in the dark, leaving the predator biting at a harmless cloud of glowing slime. This defense is highly effective, but represents a significant metabolic cost. Producing the sticky mucus and bioluminescent proteins requires days of metabolic energy. Therefore, the vampire squid only uses this glowing shield as a last resort. Most of the time, they rely on their shadowless camouflage and low oxygen tolerance to avoid detection. This combination of strategies has made them one of the most successful survivors in Earth's history. While shallow water cephalopods evolved fast bodies and short lives, the vampire squid chose longevity. They can live for several years, unlike true squids that often die after a single breeding season. Their low-energy strategy has insulated them from the catastrophic changes that occurred at the surface. When asteroids struck the Earth and collapsed surface food chains, the deep sea remained stable. The rain of organic marine snow never stopped, providing a constant source of food. And their ability to survive in near-zero oxygen allowed them to ride out global ocean anoxic events. They are living witnesses to the evolutionary power of doing less. They proved that in the game of survival, speed and aggression are not the only winning strategies. Sometimes, the ultimate way to win is to retreat to where no one else can follow, to embrace the suffocating dark and turn light itself into a shield of invisibility. When we look at the vampire squid, we see a master of deep-time survival, an ancient pacifist that conquered the abyss by mastering the physics of shadowless camouflage. The vampire squid survived 3 mass extinctions by retreating to the suffocating depths, using light to vanish, and eating what others left behind. It is not a monster, it is the ultimate master of deep-time survival. If you want to look deeper into the minds of the animals you thought you understood, subscribe. We bring you new insights every Wednesday and Saturday. Next time, the shelled cephalopod, that has remained virtually unchanged for 500 million years, and the tiny buoyancy chamber that keeps it from imploding.